All right, this is the summary to sort of tie everything together and conclude what we've been doing with these trigonometric transformations and what the graphs of these functions looks like. So our a value we know is responsible for a vertical stretch. So we could say vert stretch. Okay, a vertical stretch, and also because the amplitude is normally 1, remember the amplitude is sort of like the middle to the maximum or the middle to the bottom. So we know that the parent function fluctuates between 1 and -1. So the amplitude is kind of like half of that total range. Or it's like thinking about the middle line to the top or the middle line to the bottom, like a peak or a trough. So the amplitude of the parent function is 1. This also means that this value is the amplitude. That is the amplitude. Our parent function, for example, sine x, there's technically an imaginary coefficient of 1 there. The amplitude of the parent function is 1, whereas if you have a function like 2 sine x, that is your amplitude. And now the next value, the b value, what is that going to do to my parent function? The b value in this case will result in a horizontal compression. The reason I'm going to call this a horizontal compression, we'll see in just 1 second here. Now, important to note, you have to factor so that the x value is on its own. Make sure you have factored out this b value or this coefficient with x. Now, the reason I'm calling this a horizontal compression rather than a horizontal stretch is because it is actually flipped. It's kind of like the opposite compared to the a value. If I have a compression, it means I'm reducing my x values or I'm squishing my function together. But let's think about the difficult case where I have a fraction. If my b value was 1/2, we're actually going to stretch by a factor of 2. Why? Why would b being 1/2 result in a stretch of 2? You can see that if this thing increases and reaches its maximums and minimums at half the rate, it actually ends up taking twice as long. My c value, this is my shift. Notice the negative symbol in front, so it's kind of like a shift the opposite way. This is my shift. This is also called a phase shift, but a lot of the time I would just call it a horizontal shift, but that is a phase shift, meaning if you have sine x minus 2, you're actually going to shift it right 2, which is a bit weird. Okay, it's a bit, once again, counterintuitive because of the negative symbol. That is going to be a phase shift right 2. Last but not least, we have a vertical shift. You could call it a vertical shift. A lot of people also refer to it as the sinusoidal axis that will shift. What do I mean by a sinusoidal axis? It's actually not that weird. We can't really call it an axis of symmetry because you'll notice that if you try to reflect this, it's not perfectly symmetrical in the same way that a parabola is perfectly reflected across its axis. So we would call this an axis of symmetry. We call this a sinusoidal axis because it's not, if I flipped it, it's not an axis of symmetry. If I flipped it, I would end up with sort of like a flipped version. So this is a sinusoidal axis, which is kind of like the neutral or the almost like zero displacement, if you know what that means. Sort of like the middle ground, where it's exactly halfway between the maximums and minimums. Yeah, the parent function, the sinusoidal axis would be right at y equals 0. So this guy affects the, you could say that it's a vertical shift, right, up or down. Just this one's easy because it just takes the whole function and slides it up or down. But you could also say that it is the sinusoidal axis that is shifting. But the main thing you need to know is that it is a vertical shift. If I look at a couple of scenarios where I have fractions, this program is forcing me to use decimal numbers, so you'll just have to bear with me. But see the parent function in orange here. The green function is clearly very similar with one small change, and that change is that it is reduced to half of its maximum height and half of its minimum height. Basically, if I made a table of values, all of its y values would be cut in half. That is why the zeros do not actually change, which is important to note. But all my other values you can see are perfectly cut in half. So -1 is now only -0.5 or -0.5. Any value I take anywhere along this line, even if I took a random spot there, each spot is exactly half of the vertical displacement now. It is exactly reduced to half. Fractions as a horizontal stretch or compression, on the other hand, you have to be a bit careful. It is basically the opposite of the vertical stretches and compressions. So be careful. If you have you know it's something to do with the horizontal, you know it's something to do in the horizontal direction, but what is that 0.5 doing? My way for remembering this one is that it is increasing at half the rate. So rather than reaching the maximum by this point, it actually takes twice as long to reach the maximum. So it increasing at half the rate, you could also think about the slopes. Increasing at half the rate, it's kind of like it's getting where it needs to be half as fast. What does that turn into? Well, you can see clearly that where I normally had one cycle in 2 pi radians. That's important to note here. This is not in radians, so that's whatever, 6.28, that is like 2 pi. My parent function, clearly, that is 1 period from here to here. That is 1 period. If this graph extended, you could see that this actually is only going to complete half of a period in that same amount of time. It would actually take twice as long. So that's where it's a bit confusing. Only fitting in half would mean that it's going to take twice as long. We also say that this value, I called it earlier the b value, we also can say that based on this horizontal compression, we can say that whatever this value is, I'm calling it my b value. Whatever this b value is here, okay, in this case, my b is 0.5. We say that the period is actually going to be 2 pi, which is like 360 degrees, divided by this b value. Divided by this b value. That means that the period in this case is going to be 4 pi. I know that seems a bit weird. But it's an easy way to look at a function without having to actually graph it. You instantly know that the period is 4 pi. Be careful dividing by 0.5 or dividing by 1/2 will actually make your number larger. So you can see that the original period was 2 pi. Now the period is 4 pi. So because it's kind of like increasing at half the rate, it actually takes it twice as long to complete 1 period. All right, to sort of tie everything together, let's look at an example. I think rather than graphing, I'm going to show you the table method because it is very advantageous, I think, because you can graph it in one shot. Rather than graphing a parent function and then graphing the vertical stretch and then graphing the horizontal compression and then shifting it to the left and then shifting it down. You end up graphing this thing 4 times if you really want to graph a function with all its transformations. I'm going to show you a good method to help you out, and I think it is slightly faster. So if I have a table of values, now how can I start this out? All I need to think about is, what would my table of values look like before any transformations are on it? So let's do a simple example problem that I think summarizes everything we need to know. If I have the function f at x equals 2 sine, I've already factored it, we'll say x minus pi over 2. I'm going to do this pretty briefly because I think I can sort of cut to the chase here. But the long story short is that if I have my x and y, let's think about the parent function. What are my values going to be for the parent function? All you need to do is use your unit circle. So if you don't know where these values are coming from, make sure you use your unit circle. At 0 radians, my y value, my sine value, is also 0. This is how I would graph, this is how I would graph sine x, right? Okay, moving up to 30 degrees or pi over 6, I would have a y value of a half. If I keep going, or really you can pick any number of data points you'd like, if I keep going, I would get my standard unit circle values, right? So I'm just going to do these 3, and we'll see if we can get the point across. All I have to do if I'm trying to figure out what the graph of this big red function up top would be, it's pretty complicated looking, but if you take it one step at a time, it's actually not too bad. What is this going to do? That is a vertical stretch, so I go to my y values and I stretch them. I'm going to double my y values. That's it. Now I'm one step closer. If I were to graph this now, this data table, I would have the function 2 sine of x. That's it. That's all it would take. Now, what's my horizontal stretch or compression going to do? I have a half. Remember, that one is kind of counterintuitive. That is flipped. I call this one a compression so that you remember it's not the same as a stretch. A half means that I am actually going to double my x values. So it's kind of like the opposite. It's a bit weird. This 2 and this half are both turning into stretches by a factor of 2. So be careful of that one. That one's probably the only tricky step about this. Now let's go to my phase shift or my horizontal shift. I have a value here. Remember, it's almost like we ignore the negative symbol, or we just look at it with the negative symbol and flip it. So this is a shift of pi over 2 to the right. Well, if I'm talking about left and right, I'm definitely referring to the x direction. So I actually will have to add pi over 2 to each of these. Plus pi over 2, a little bit messy, I apologize. Okay, and remember order of operations. When you go to solve these, make sure you do your multiplication before any adding or subtracting. Lastly, I have my vertical shift, or I'm changing my sinusoidal axis. I can take away 1 from each y value because it's a vertical shift. If I go ahead and do this, I will get my new data table. If I do this, I should get my new data table. When you get your new data table, I'll just do the first 2, and I think you guys will get the point. So 2 times 0, well, that's easy, it's 0, plus pi over 2. My y value here, I have 0 times 2, right? Order of operations, always do your multiplication first. So 0 minus 1. That is my new data point compared to the parent function. On to the next point, I have 2 times pi over 6. That is like pi over 3. Pi over 2 plus pi over 3. You do need a common denominator in that, so that would be 3 pi over 6 plus 2 pi over 6, for a total of 5 pi over 6. My y value, 2 times a half is 1. 1 minus 1 is 0, and so on and so on. If you do that, you can graph it in one shot rather than graphing multiple curves all on the same graph. Both are equally valid, and I think it is important to start by graphing, doing lots of graphing each transformation one by one. But as you get better and more advanced in the course, you're going to want to just use a table probably so that you can graph it in one shot.